Hello everyone. We want to continue on our analysis of transients for second and first order circuits, and we want to do some examples in this lecture. I want to go through first the differential equation, second order differential equation for the series RLC case. So we covered an example of the parallel RLC case last time. I want to do the series RLC case now. So the circuit we said is going to look something like this. So I have a voltage source, and I have a resistor, inductor, capacitor, and I'm solving for the current, loop current going through the circuit. So the natural thing we can apply here is KVL. And KVL gives me the following equation. So I have Ri, that's the voltage across the resistor, and then I have L di by dt, that's the voltage across the inductor, and then the voltage across the capacitor is just in relation to I is just going to be the integration of I. So it's going to be 1 over C integral from t0 to t of I dt plus the initial condition of the capacitor voltage. So let's try to put in here Vc t0, right? So that equals Vs t. And to get the second order differential equation, we just differentiate both sides. So we end up with L d square I over dt squared plus R di by dt. When I differentiate the constant, it turns to 0. And then I differentiate this term, I essentially invert the integration, and I end up with I over C. So this equals dVs over dt. Okay, so now we compare this, we contrast this with the general form for, first let me divide everything by L actually. So I end up with this equation, d square I over dt square plus R over L di by dt. Oh, this is a plus here, plus I over LC equals 1 over L dVs by dt. Okay, so this is the kind of differential equation that I would get, and then we solve the, of course, we solve the homogeneous equation, and then we can then solve the particular equation depending on what the source is. Right, but let's find out what for this example, what would the damping factor be, and what would the undamped natural frequency be. So let's compare it to the general differential equation. It's going to be d square x over dt square plus 2 zeta omega naught dx by dt plus x over L omega naught squared x equals 0. Right, and compare the constants. So I would compare this to this, and then I would compare this to this. We get the same result as far as omega naught is concerned. Omega naught squared here turns out to be 1 over LC, so omega naught will be 1 over square LC, square root LC. But zeta will be different. The damping coefficient will be different compared to the case of the parallel RLC circuit. Right, so let's compare. So we have 2 zeta omega naught equals R over L. So we end up with zeta naught equals zeta equals half R over L 1 over omega naught. We know that omega naught equals 1 over square root LC, so this becomes half R over L square root LC. We end up with zeta being half R square root C over L. Notice that this is this contrasts with what we got for zeta for the case of the parallel RLC circuit. Is different. It's the reciprocal of this, except the square root of 2. I mean, it doesn't matter. What matters is that this is still a dimensionless quantity, right? It makes sense from that point of view, and it represents the zeta constant for a series RLC circuit. What I'm trying to say is that zeta might not necessarily be the same for any circuit, right? You just have to solve the differential equation for any particular circuit to find out what zeta is going to be for that particular circuit. Okay. Omega, on the other hand, mostly omega will tend to be 1 over square root LC. Mostly, I mean, most cases, not all cases. Sometimes you have circuits that are second order that have like 2 capacitors like this. So those will not show up as 1 over square root LC. Those will be different. You have to solve the differential equation for those circuits. Okay. So this is what zeta is going to be for the series case and what omega naught is. All right, let's solve some examples. The first example I want to solve is example 7.8, which is a series RLC circuit. So it's a series connected R L C circuit. There's no source, but there has to be an initial condition, either a voltage initial condition or a current initial condition, or both. Typically, for a second order circuit, you need two initial conditions, right? Or one initial condition and the rate of change of that initial condition, right? So an example is given where we have an RLC circuit series connected, where the initial inductor current IL0 is 4 amps, and the initial capacitor voltage VC0 is minus 4 volts. And then the values for the circuit parameters components are L equals 1 Henry, R equals 6 ohms, and C equals 0.4 farads. Okay, we said that the differential equation is as follows: d square I over dt squared. In this case, there is no voltage, so there is no forcing function. So I just have to write the left-hand side that I've derived here, this equation. So this is going to be R over L di by dt, and then plus I over LC equals 0. And we said this tells us that omega naught equals 1 over square root LC. So it's going to be 1 over square root L is 1 and C is 0.04. Right, so this is going to be 1 over square root 0.04 essentially, which is 4 over 100. I can simplify this further, it's fine. So this is going to be 1 over 2, or square root of 4 is what? Is 2, and square root of 100 is 10, of course. Right, multiply this by 10 over 2 times 10 over 2. Just doing simplification, I end up with 10 over 2, which is 5. So omega naught is going to be 5. Okay, what about the damping factor? We calculated the damping factor here, the equation for the damping factor here. The damping factor is half R over L, or half, sorry, it's here. Half R C over L, right? Half R square root C over L. Right, half, we said R is what? 6 ohms. So half, and then square root C over L. C is 0.04 farad, L is 1 Henry, right? So same deal, I just want to simplify this now. Square root of 3, square root of 4 over 100 equals 3 times 2 over 10. So this is 3 times 2, 6 over 10, 0.6. Zeta is 0.6, which is less than 1, right? So this means this is an underdamped, I don't know how to spell damped anymore, underdamped system, circuit, right? Meaning it will exhibit however the circuit behaves, it will exhibit some oscillatory phenomena behavior. It is underdamped, right? So we should expect the roots of the characteristic equation to be complex conjugate, and when we find the roots of the characteristic equation, they will turn out to be complex conjugate. Okay, we don't need to do that. We know it is going to be underdamped, right? But I guess we can do that for completion purposes, just to do it. But I could take this equation, which is what? Let me plug in the numbers. This becomes d squared I over dt squared. What's r over L? R over L is 6 di by dt plus I over LC, which is omega squared. Omega naught is 5, omega naught squared is 25, I equals 0, right? So I can solve the characteristic equation for this, which is lambda squared plus 6 plus 25, lambda squared plus 6 lambda plus 25 equals 0. In the book they use S instead of lambda. It's the same thing. I prefer to use lambda because S has a specific meaning in the Laplace transform. I don't want to confuse the matter. Right now we're not talking about the Laplace transform, we're just talking about solving the characteristic equation. If you want to use S or lambda, it's fine. My choice is to use lambda to represent the independent variable in the characteristic equation. Right? So noting that zeta is less than 1, if you wish, you can find the roots of the characteristic equation, and they turn out to be complex conjugate. They have to be complex conjugate, right? Because why do they have to be complex conjugate? Because zeta is less than 1. So what we could do is and again, we could solve this by using the quadratic formula, or we could complete the square, which is what I prefer to do, right? So this is lambda squared. This is going to be 2 times 3, right? Lambda. We can consider this to be 2 times 3 lambda. So that means that the second term should be 3. So I should be I can add, what's 3 squared? It's 9. So I can add 9 here, which is 3 squared. And then I can subtract 3 squared plus 25, and I get the same thing. So this is the act of completing the square. I want to get something here that is in square form, right? And I can, instead of this, I can write lambda plus 3 squared, right? I get the same thing. So this is lambda squared plus 3 squared plus 2 times 3 times lambda, which is 6 lambda. And then I end up with plus 25 minus 3 squared plus 25 minus 9. 25 minus 9, of course, is 25 minus 10 is 15. So 25 minus 9 is 16. So this becomes plus 16. So we end up with lambda plus 3 squared equals minus 16. And you can see instantly that now we will get complex conjugate solutions for this second order equation. When I take the square root, I end up with lambda plus 3 equals minus, what's the square root of 16? 4. J, because it's negative, right? I take the square root of negative 16 and the positive and negative value of that, right? Because it's a square root. And then that tells me that lambda 1 and 2 are equal to minus 3 plus minus J4. So lambda 1 is going to be minus 3 plus J4. Lambda 2 equals minus 3 minus J4. Okay. So as I expected, because data is less than 1, the characteristic equation has roots that are complex and conjugate. Okay. So what happens? So from the step-by-step strategy, what happens? What's the form of the response when the system is underdamped? Let me write it down. So in that case, we're solving, by the way, for I. We said we're solving for I, right? So the form of response is going to be as follows. I of t is going to be E minus sigma t. Just plugging in, writing down the equation. A1 cosine omega d t plus A2 sine omega d t, where sigma gamma omega naught is zeta omega naught, and omega d is just simple omega naught square root 1 minus zeta squared. Right? So zeta turned out to be what? Zeta turned out to be 0.6. And then omega naught turned out to be 5, right? So it's 0.6 times 5. And then this is going to be 5 square root 1 minus 0.6 squared. So this is going to be, well, 0.6 times 5 is like 0.6 times 10 over 2, which is 6 over 2, which is 3, right? So this is sigma. And then omega d is just, let's do this, square root 1 minus 6 over 10, which is 6 times 6 is 36, over 10 squared, which is 100, which equals 5 square root 100 over 100 minus 36 over 100 equals 5 square root 100 minus 36 is 64 over 100. So you end up with 5. What's square root of 64? 8. And square root of 100 is 10. So you end up with 40 divided by 10, 4. So sigma d, omega d is 4. So now we can apply the general form of the solution of the response when we have an underdamped case, and from the steps that we described earlier in an earlier lecture, this response is going to look like this: x of t. Well, in this case, it's I of t. So I of t equals e minus sigma t, which is what? Which is e minus sigma is 3, e minus 3t. Then we have a1 cosine omega d is 4, cosine 4t plus a2 sine 4t. Right, this is the response, and all that is left now is the matter of finding the constants a1 and a2, and those we find from the initial conditions. Right, the first initial condition we could apply is the current initial condition, right? So we know that I0 equals what? I0 equals, we have it here, I believe. I0 equals 4 amps and VC equals minus 4 volts. Let's start with I0. So that tells me that 4 amps e to the power 0 is just 1. And then yeah, so 4 equals A1. Cosine 0 is 1, right? Just 1, nothing more. Plus sine 0 is what? Sine 0 is 0, right? So I'm starting at t equals 0. So e to the power 0 is 1. and then cosine 0 is 1, and then sine 0 is 0. So I have a2 times 0, 0. So a1 equals 4. This is the first constant that we found. How do we find the second constant? Well, we have the other initial condition that we have is the capacitor voltage, right? So we kind of like need to apply KVL. We know the inductor current. We solved for I, right? So we kind of need to apply KVL on this loop to solve for the capacitor voltage, and then we use the initial condition on the capacitor voltage. So we need to solve for VC of t, right? So what is VC of t? Well, let's write the KVL equation for this loop. So the KVL equation is going to be, let's do the loop, I guess, this way. So this is going to be IR, right? This is R, and this is going to be plus minus VL, and then we have VC. So IR plus VL plus VC equals 0. So that tells me, well, what's VL? VL we know is just L di by dt, right? That's the equation. And then IR plus VCT equals 0. Let me put this the other side. This is equals minus VC of t. So that tells me VC of t equals minus IR minus L di by dt. Right? Why do I want to solve for VC of t? I want to solve for VC of t because the other initial condition is given in terms of VC. Right? But this is fine. I already know what I is. So I just plug it in there. So I end up with what's R? R is 6 ohms, right? R is 6 ohms. So I plug R in there. Right? Let me put in plug in I. So this is minus 6 E minus 3 T. We already know what A1 is. A1 is 4. 4 cosine 4T. And we're solving for A2. We don't know what A2 is yet. Sine 4T. Right? This is the first term. And then the second term is minus L. What is L? L is, I forgot what is L. L is 1 Henry. So that's simple enough. It's just 1. Right, and then di by dt. I want to take this I and now differentiate it. Right, so this is kind of like we have to do this differentiation. Right, so we have, it's a product, right? So I have to take, right? So I have to take 6, sorry, not 6. I have to take e to the minus 3t, differentiate it. So I end up with minus 3 e to the minus 3t, right? That's how they differentiate the exponential, times 4 cosine 4t plus a2 sine 4t. I'm applying the product rule here, right? And then I take plus e minus 3t, and then I differentiate the second term and the product, which is going to be, cosine is going to turn into minus sine. It's going to be minus 4 sine 4t, and I differentiate the thing inside the sine. The cosine is going to be 4, so it's going to be minus 16 sine 4t. And then the other term is going to be plus 4a2 sine 4 of t. Right, so it's a bit of an involved formula, but we can evaluate it. So VC of t equals, let me clean it up. It's minus 6 e minus 3t, 4 cosine 4t plus a2 sine 4t, and then move the sign minus n. I end up with plus 3e minus 3t multiplied by 4 cosine 4t there is no parentheses here, right? Plus a2 sine 4t, and then minus e minus 3t minus 16 sine, oh, I made a mistake here, sine, when I differentiate sine I get cosine, okay? Minus 16 sine 4t plus 4a2 cosine 4t. Right, so this is the expression I'm trying to find. Let me, I guess I can sum it all up now. So let me sum everything up. Let me sum so I can move the exponentials inside the brackets, the parentheses, and then I can collect the sines and cosines. Right, so I end up with what? I end up with as far as the cosines are concerned, I end up with minus 6 times 4, which is what? Minus 6 times 4 is minus 24, right? And then the other cosines here is going to be 3 plus 3 times 4, which is 12, plus 12, and then minus 16. So, oh, this is not a cosine, this is a sine. This is a cosine. So minus 4 a2, right? And then we will have e minus 3t cosine 4t, and then the other term is going to be, I correct all the factors in front of the sign. So I have minus 6a2, right? Minus 6a2, and then plus 3a2, and then minus times 4, I end up with minus 4a2, and this is e minus 3t sine 4t. I collected all the terms for the sine. So I end up with the VC of t being, let me simplify this. This is going to be minus 4a2, 12 minus 24 is minus 12, e minus 3t cosine 4t. And then minus 6 minus 4 is going to be minus 10a2 plus 3 is going to be minus 7a2 e minus 3t sine 4t. Okay, VC0 we said equals minus 4, and I just plug in t equals 0. Sine 0 is of course 0, cosine 0 is 1, e to the power 0 is 1, so I end up with minus 4 being equal to minus 4a2 minus 12, divide everything by minus 4, I end up with 1 equals a2 plus minus 12 over minus 4 is going to be plus 3, so a2 is going to be equal to minus 2. Okay, so I go back to the equation for I, and I just plug in a2, a1 we found to be 4, a2 we found to be minus 2, so the equation for I of t becomes I of t equals e minus 3t 4 cosine 4t minus 2 sine 4t amps. And then if we want, we can write Vc of t equals e minus 3t, right? And then I have to plug in the value for, where's the expression? Here's the expression. So a2 is minus 2, so it's going to be minus 4 times minus 2, which is going to be 8, minus 12. So going to be minus 4, so it's going to be minus 4 cosine 4t, and then this expression here is going to be minus 7a2, minus 7 times minus 2 is going to be, 7 times 2 is 14, right? So it's going to be plus 14 sine 40. I believe there's a typo here in the book. They have 22, but I mean, my calculation doesn't show 22, so I'm going to assume there's a typo. Okay, so this is going to be volts. Okay, so this is the current in this series RLC circuit, and this is the voltage across the capacitor. And then if you plot the current, you will get, of course, an oscillatory response. You will get something that looks like this. You will get something like, first, the initial condition for the current is going to be, as you expect, 4, right? T equals 0 is going to be cosine 0 is 1, sine 0 is 0, and then e to the power 0 is 1. So you end up start with 4. And then you will get something like this, something that will oscillate until it settles down. What's the settling point here? The settling point is the value of I at infinity, right? In this case, it's going to be what? It's going to be 0, right? Because e to the minus t, as t goes to infinity, the envelope is going to go down to 0. The thing that multiplies the sinusoidal form of the solution is going to go to 0. So the steady state of the circuit will be 0. Another way of saying that, describing that physically, is that all the energy in the circuit, in the capacitor and the inductor, is going to oscillate. The energy in the circuit is going to be oscillating between the inductor and the capacitor. But in the meantime, also, that will be dissipating in the resistor, and ultimately all the energy will go back and forth until it dissipates fully in the resistor. That's why things settle down to 0. Okay, and this concludes this example. Let's do another example. So I'm gonna do example, which one? Example 7.9 in the book. Slightly more involved example. It's a circuit that's neither a series connected circuit or a parallel connected circuit. It's kind of like a mix of the two. So example. All right, so given a circuit that looks like this, we have the inductor L, and then the inductor goes through a resistor R1. We're solving for the I and the V, right? So the inductor current goes into a resistor R1, and then it splits into a capacitor. So this is V, and another resistor R2, right? And then it goes back. So this is a circuit with two meshes. So we have mesh 1 and mesh 2. This is the topology of this circuit. The given parameters are R1 equals 10 ohms, R2 equals 8 ohms, C equals 1/8 of a farad, and L equals 2 henries. And the given initial conditions are V0 equals 1 volt, the voltage across the cap, and then I0, which is the inductor current, equals half an amp. All right, so we want to get the differential equation representing this circuit. So we could apply both KVL and KCL. I mean, whatever method you want to use, it has to be a method that makes sense, of course, but whatever method you want to utilize, you can utilize to get the differential equation. There's no hard rule on what method to use. You have to explore the different available methods. The simplest methods we could use, of course, is KVL and KCL. If it was a more complicated circuit, you might consider, let's say, using mesh analysis or nodal analysis, so on and so forth. Okay, but let's use KVL. Let's use KVL on this loop, and let's use, this is KVL, and let's use KCL on this node. Okay, so using KVL on this loop, we start with the voltage across the inductor. It's going to be L di by dt plus the voltage across this resistor is going to be R1I. And finally, we have the voltage across this capacitor. It's easy. Plus V equals 0. So this is applying KVL. And then I want to apply KCL to this node. So I need to write down the incoming current into the node I as equal the sum of the outgoing currents. Right. So applying KCL gives me I, the incoming current, equals the outgoing currents, which is C dV by dt. That's the capacitor current. And then the resistor current is V over R2. Okay, so this is equation 2. Now what I could do is I could just take equation 1, and I know what I is. I just substitute I into equation 1. And that gives me the second order differential equation that I need to solve. So I'm solving for the voltage. I'm choosing to solve for the voltage. I could have chosen to solve for the current. That's fine. But I want to solve for the voltage. Okay, so let's plug I in. So I take now L times C. So the first step is differentiating this term with respect to t. So this becomes LC, and then I have a second derivative, V over dt squared. Then I'm differentiating this. So this is plus L over R2 dV by dt. Then plug in I here, I end up with plus R1C dV by dt plus R1 over R2V, right? And then finally I have plus V equals 0. I collect all the terms, so I end up with LC d squared V over dt squared plus I separate the terms from dV by dt. I end up with L over R2 plus R1C dV over dt, and then those are the terms with V, so this becomes R1 over R2 plus 1 V equals 0. I could write this as R2 over R2, so I end up with R1 plus R2 over R2. Okay, and I can divide everything by LC to get the second order differential equation in the normalized form, where the coefficient of the highest order is 1. So I end up with d squared V over dt squared plus, I'm dividing by 1 over LC, so I end up with 1 over R2C plus R1 over L dV by dt plus R1 plus R2 over R2 LC V equals 0. Okay, and this is the differential equation. Notice instantly that, remember when I said that mostly you will find, in most situations, you will get omega naught equals 1 over square root LC, but in many cases it won't. It will depend on the circuit. This is an example where omega naught depends on the circuit. Omega naught in this case is going to be square root R1, this term, square root of this term. So it's going to be square root R1 plus R2 over R2 LC. So it has LC in it, but it has other terms. Right? And what about zeta? Zeta is going to be, well, 2 zeta omega naught is equal to 1 over R2C plus R1 over L from the differential equation. So omega naught equals half this term times the inverse of omega naught, which is, oh, this is zeta. Inverse of omega naught is going to be, this is R1 plus R2. Let me write this clearly. R1 plus, oh, no, the inverse of it. So this is going to be R2 LC over R1 plus R2. Okay. So this is omega naught and this is zeta for this example. What's omega naught? Let's evaluate it. So it's R1 plus R2. R1 is 10, R2 is 8. That's square root 18 over R2 times L times C. So 8 times 2 times 1 over 8. 8 times 2 times 1 over 8. That ends up being square root of 18 over 2 square root of 9, 3. So omega naught is 3. Okay. Zeta equals half. What R2, I have to keep reminding myself, R2 is 8 and R1 is 10. So it's 1 over 8 plus R1, 10, and then C is 1/8 and L is 2. C is 1/8 times 1/8 and L is 2. So I end up, oh, and then the inverse of this term is the inverse of omega naught, right? Which is 1 over 3. So I end up with half times 1 plus 5, 6 times 1/3. So this becomes 6 over 6 equals 1. So this is a case where zeta equals 1. The system is critically damped. Okay, the system is critically damped. What did we say the natural response? What did we say that the response equation would be for a system that's critically damped? Well, it has the following form. It's like K1 E minus zeta is 1, right? Omega naught T, right? Plus K2 T E minus omega naught T. This is the form that we discovered, right? So V of T equals K1. Omega naught is 3. So then be K1 minus 3T plus K2T E minus 3T. Now it's a matter of using the initial conditions to find the constants K1 and K2. So let's start with the voltage initial condition. So we know that V0 equals 1 volt, right? That was the initial condition. V0 is 1 volt and I0 is half an amp. Okay, so substituting in V0 equals 1 volts, right? T equals 0, so it becomes K1 e to the power 0 is 1 plus K2T e to the power 0. 0 cancels out this whole term, so we end up with K1 equals 1. Right, and we found the first constant. So Vt should equal E minus 3t plus K2t E minus 3t. Okay, now the other initial condition is given in terms of the current, and we have an equation for the current here, right? I think we calculated an equation for, oh yeah, we calculated an equation for the current here. So we just use it to calculate the current from our calculation of V, and then we apply the initial condition to that equation. So I equals C dV by dt over plus V over R2. So I equals C dV by dt plus V over R2. And then what's dV by dt? dV by dt is just going to be minus 3 E minus 3t. And then here we have a product of t and E minus 3t, so we need to apply the product rule. So that will be plus K2 E minus 3t. I differentiate the t, and then I differentiate the exponential. This will be minus 3 K2 t E minus 3t. So dV by dt is going to equal, let me take the E minus 3t out to simplify. It's going to be E minus 3t times minus 3 plus K2 minus 3 K2t. And then finally, I is just going to be C times dV by dt. C is 1/8, right? So it's going to be 1/8 E minus 3t minus 3 plus K2 plus 3 K2t. And then V, which we calculated, is going to be plus E minus 3t plus K2t E minus 3t, this whole thing divided by R2. R2 is 8. So plug in I equals 0, T equals 0, which is half an amp. This simplifies things, right? This term goes away, this term goes away because T equals 0. And I end up with 1/8 e to the power 0 is 1 minus 3 plus K2, right? Plus e to the power 0 here is 1. So I end up with 1/8. Multiply both sides by 8, I end up with 8 over 2 is 4, so 4 equals minus 3 plus K2 plus 1. Move 3 to the other side, becomes 7. Move 1 to the other side, becomes minus 1, so it becomes 6. K2 would be 6. Right? So the final form of the solution will be V of t equals K1, which is 1, E minus 3t plus 6t E minus 3t. Okay, if we plot this, it will look something like this. Because we're starting with t equals 0, this whole term cancels out at the beginning, but then as t increases, we start to go up a bit, but then the exponential takes over. So this is not exactly oscillatory, this is at the critical point between oscillation and just a damped response. Okay, so this is this example. I want to talk about what we have covered in our analysis up to this point. As I said in a previous lecture, we covered situations where the circuit is in some stable condition, some steady state condition previously. It goes into a transient, right? And then it reaches steady state, and we have our method of analyzing those transients where we use the steady state pre-transient to figure out where the circuit is, and then use that as the initial condition for the transient to solve for the transient, and then we figure out the steady state of that transient. So this is like a method of analysis, and this allows us to analyze a lot of circuits under a lot of transients. If the transients like happen in a certain time, at a specific time, let's say something like this, right? If the transients happen at a specific time, and the circuit is at steady state before the transient, and then a steady state after the transient, and then any sources in the circuit have to be DC sources, maybe meaning they are constants. We still don't know yet how to analyze any transient in general for right, any transient in general for non-DC sources. Right, we will know how to do that once we go a bit more deeper into AC analysis, sinusoidal analysis, and ultimately go into the Laplace transform, which allows us to analyze transients and circuits for any general forcing function, any general source that is acting on the circuit. Right. Having said that, even with the very specific tools that we developed to this point, we still could handle more than a single transient, right? We could handle, if we still have DC sources, we could still handle cases where we have like a transient, and then we suddenly have another transient, right? And then suddenly have a third transient, and then we reach steady state, right? So those kind of cases are easy to handle with the tools that we have at hand. Why? Because the tools that we have in our hand allows us to analyze any circuit and solve for it as long as we know the initial conditions. So what we could do is we could solve for the initial conditions here and use that at the start as the starting point for finding the response in this region 1. And then since we know the response in this region, we can solve for the initial condition here in it 2 and use that initial condition to solve for the transient in this region 2. And because we know the transient in this region 2, we can solve for the initial condition here at this interface at this point in time and use that to find the transient in region 3. So we have already the tools to handle multiple transients, provided that the DC sources, the forcing functions, remain DC. Okay. How we handle general forcing functions, starting with AC, sinusoidal, and then more general. That's what we will cover during the big chunk of this course, like the which is will be the Laplace transform and at the end, and then sinusoidal analysis that we will do next. Okay, so but in the intermediate we could still do this kind of analysis, and to help us do this kind of analysis, there's a mathematical function that we want to introduce called the unit step function. The unit step function is also called the Heaviside step function. Is a very simple function. It's a function that's 1 at t larger than 0 and 0 for t less than 0. That's what it is. And if you plot it with respect to time, it will look something like this. Okay. This is a kind of function allows us to model any forcing function that has discontinuities in it. Right? So any function, let's say voltage V of t, that looks like this, it has discontinuities in it. We can model with the units, what's called the unit step function, right? And this kind of thing, we can analyze the response of the circuit to this kind of thing using the tools that we already know, right? Because we can figure out the initial condition in this region, we can find the transient, then figure out what the initial condition will be in the new region when the transient reaches this point, and then solve the second transient and so on and so forth. Okay, and the unit step function provides us the tool for doing that. Right. So it's a dimensionless function. It doesn't have units of voltage or current. You let's say you tie it with voltage signals and current signals to get this continuous effect, right? So let's say I have a voltage source that starts at 0 and then goes to 5 volts, steps up at t equals 0. Then I can model it as 5 u of t volts. That's the role of the unit step function, to provide a mathematical model of modeling, to provide mathematical means of modeling discontinuities in the voltage and the current. So the step function is one of two singular functions that we will study. Singular means like opposite of continuous, not continuous. And you know what continuous functions are from calculus, right? They are smooth functions that do not change suddenly. They don't have kinks. They don't change suddenly, and they don't have kinks in them like this. Oh, sorry. Functions that don't have kinks in them are differentiable functions. This is still continuous. Okay, forget I said that. This function. So this function is smooth. It's continuous and differentiable. This function is still continuous, right? But it's not, so this function is not differentiable, but it's still continuous because there are no jumps in it. Non-continuous functions are functions that have jumps in them. So if you have a function that has a jump in it like that, that's a non-continuous function. Okay. So U of t is really all we need if we want to model any discontinuities in a signal, in a voltage or a current. One major kind of discontinuity that is very useful is what's called a pulse. So if I have some f of t that's 1 for a certain period t and 0 otherwise, that's called a pulse. And I don't need to define a new function to build a pulse. I can just build a pulse from two step functions. So I can take one step function u of t and then take another step function that's shifted in time by an amount t. How do I shift a function in time? I do this, right? Ut minus t capital, and then I subtract them from each other. And when I subtract them from each other, I get the pulse, right? So the pulse of t is just going to be u of t minus u of t minus t. That's it. And a pulse of any magnitude, if the magnitude is not 1, let's say the magnitude is a, is going to be as follows. The pulse of any magnitude, let's say I have a voltage that is a pulse of magnitude a, so this is v of t, is just going to be a times the pulse unit pulse function, which is u of t minus u t minus t. Okay. So I want to show you one example of how to do this analysis, where we have instead of one transient happening, we're solving for multiple transients, and we're always recalculating the new initial condition to find the new transient. Right, this is easy to do. I'll just show you an example how to do that, and how can we use the step function to just represent those things mathematically, those discontinuities mathematically. So I want to do, if we have time, I want to do example 7.6. Source V of t, it connects to so we have a capacitor V of t, and then I have 4 kilo ohms, then I have an 8 kilo ohms, and then the circuit variable that I'm solving for is this, what's called the output VO of t. And let me see, the input, here's where the pulse comes in. The input Vt is defined to be this pulse. It's defined to be, so this is in seconds, and this is Vt in volts. It's defined to start at 0, go up to 9 volts, and then at 0.3 go back to 0. So we would represent it mathematically using the help of the unit step function as follows. So it's going to be 9 of t minus u of t minus the period here, which is 0.3. Right, I could write it as follows: v of t equals 9 u of t minus 9 u. Let me write this more clearly. 9 minus 9 u of t minus 0.3. Okay, volts. What are the parameters? What's the capacitance? The capacitance is the capacitance is 100. Seems to be 100 microfarads. Okay, the capacitance is 100 microfarads. Okay, so the techniques that we learned up to this point apply even though you have multiple events happening and it's just like I said, it's just you have to take it one by one. You have to take first find the transient in this region, right? And after you find the transient in this region, you have the initial condition, and then you have the transient in this region, and then you use the transient in this region to find out what the response is going to be at this other edge, at this other transient event, and then you use that value as the new initial condition, and then you find the transient in this region. Okay, so that's how you will solve this problem. Right. So initially, what is the capacitor voltage? Right. So we said so our first transient occurs at t equals 0. So we have two transients. It's like we're solving two transient problems. First transient occurs at t equals 0, and the second transient occurs at t equals 0.3. Okay. So what happens initially? Initially, before t equals 0, the input was 0 for an infinite amount of time. So we assume that the circuit was already at steady state. Because the circuit was already at steady state, the capacitor voltage is the capacitor is going to act as an open circuit. So for t less than 0, the circuit is going to look like this. We have a voltage of 0 represented by a short circuit. The capacitor is an open circuit, so it's really 0, right? And then oh, there's a resistor here, and then there's a resistor here, and there's a resistor here. So really, there's no source, so the output voltage is 0, right? So VO 0 minus is 0, right? And VC 0 minus is 0. We need to keep track of how the capacitor voltage changes, because the capacitor voltage is the variable that's going to remain continuous, is the variable that's not going to change before the transient and after the transient. It will maintain its value just before the transient and just after the transient. Yeah, I think I wanna, with a little bit out of time, I want to complete this example in the next lecture. All right, guys, thank you.